Okay, so let's continue our lecture today. So, uh, okay, so yeah, so let me start with the position where I left last time. So about the uh, control for the lower bound of the lattices. Okay, so say you have okay, so here we have like this lattice omega 1, and then we can scalar it by like a factor of like n1. Okay. And then we have this omega 2. Okay. And then we can scale it by n2. Okay. So okay, so let's break it into cases. So first, let's say that this omega 1 and omega 2, they are in the same quadrant. Okay, so namely, if after some rotation, this omega 2 it also either lies in the first quadrant or it lies in the fourth quadrant. Okay. So in this case, so what I have is that so okay, so I would have, so then the x component and the y component, they are added, right? So for the W2 plus W1. So then what I get is that okay, so then they're added, and then that becomes like a triangle, right? So does that have something to do with the factors? Okay, let me see. So okay, so suppose we have W1, sorry, omega 1 is equal to x1 plus iy1, and omega 2 is equal to x2 plus iy2. So therefore, okay, so then omega 1 plus n1 omega 1 plus n2 omega 2. Okay, so here this n is any real number. Okay, it doesn't have to be an integer. So it's equal to what? It is equal to so okay, so n1 x1 plus n2 x2, yeah, plus I times n1 y1 plus n2 y2. Okay, so now you take the modulus of this whole thing. Okay, so yeah, so you are adding the x component and then you are adding the y component. Okay, I think it has something to do with the angle here, I think. Okay, so so let's call this angle theta here. Okay. So okay. Okay, so if you go it further, wait. Okay, I think this I think here this N1 and N2, right? So this N1 and N2 is somehow kind of control the angle here. So you can think of like as I getting like further and further, then this one would, so this angle would kind of goes down, right? So it would like that. Yeah, so imagine that you're going there and then, wait, does the angle goes, so naively speaking, wait, I was a little bit confused here. So would the angle go down or go up? Or keep the same? Okay, so suppose that you have a point, let's say 2, 0, right? And then you have a point, let's say 1, 1. And then when you add them up, you get a point that has direction 3, 1, right? Okay, so now, okay, so first point, and then second point, say that you have a point 4, 0, right? And then you still keep the same 1, 1, and then you adding it. Okay, so the angle definitely is decreasing, right? So why is it decreasing? Because the slope has changed, right? The slope, yes. So the slope has been changed down, right? So in this case, yes. So this angle theta is really like the slope, right? It's like the, yes. It's like the ratio between the these two values, right? So yes, it's like the y over x over y, right? Or y, sorry. So which one is the other one? So if you increase x more, then yeah, y over x. Okay, so y equal to, yeah. So okay, yeah. So okay, so here this slope is getting a little bit different here. Okay, so and then what we do, so okay, so then what do we do? So as okay, so okay, so okay, so the slope, okay, 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 so in this case the slope, yeah, so here I'm interested in the hypotenuse, right? Yes, the hypotenuse. So I want to find a constant k, right? Such that for any yeah. So basically for any n1 and n2, so this is always so this lower bound is always whole, right? Yeah. So why there is a uniform bounce? Let's see. So first, this omega 1 and omega 2 are fixed, right? So let me think. Okay. So suppose that you are having, let's see. So suppose that this n1 is like very small, right? Okay, so let's break it in the first situation. So condition A, so suppose that if this n1 is small, then you are having the n2 very big, right? So in this case, how will this behave? So this will behave like so if you have n1 small, then you increase the n2. Wait, shoot, what I'm saying. So yes. So if you unfix, okay, unfix. Okay. So namely you just increase in this direction. Okay, so eventually the so the ratio, okay. So what happens is that the ratio will goes to 0, right? As this n2 goes to infinity, right? So so namely what you get is that so yeah, so you may imagine the length of the triangle is like is something like just the length of the so the length of the hypotenuse is really close to the length of the baseline, right? Yeah, because this one is fixed. So therefore, yeah. So what is the argument? Yeah. So basically, you are having. So think of that. So think of this. So think of this as just the, just the. Yeah. So this one is just x1, right? Okay. All right. So okay. So yeah. So this one is just x1. So there's no y1 here. So times I n2 I2, okay. Yeah, so namely okay, so so you will have, let me see, so you will have n1 x1. So the x1 is like what? X1 is really big, okay. And then plus a fixed number. Okay, so n2 x2. Okay, I think you can definitely you can definitely show that. So this is like the very long edge. You square it, you plus a fixed number, which is n2 y2, right? So we are having the n2 fixed. Oh, sorry, I think I cannot reverse it. So this should be the n2 is the one that's being fixed, right? sorry. Yeah, I mean to fix the smaller. Fix the W2. Okay, or omega 2. Sorry. Yeah. Okay. So plus n2 squared, which is equal to the hypotenuse. Let's say L squared. Okay. Yeah. So this is a fixed number, and then as this we increase. Yeah, so the ratio, okay, so how am I gonna say? So if I make this one bigger and bigger, so this one is also fixed, right? So if I make this one bigger and bigger, so the whole thing will just yeah, so eventually the limit will goes to 1 eventually. Yeah, okay, yeah, okay. All right, so yeah, so the limit of this whole thing, L, as a denominator, and the numerator will be just these copies, and then you take the limit as n1 goes to infinity. This limit actually goes to 1. So therefore, this just indicates that this one is just, so the hypotenuse is behaved like this one. Okay. All right. So yeah. So in this case, what would happen here? So in this case, okay. So what would the k be in this case, right? So say that. Okay. Okay, I think I have to make another hypothesis here. So let us assume that what do you assume? Okay, let us assume that this is equal to 1. Okay. And then this omega 2 is equal to what? Let's say let's say this was 1 plus I. Okay. Let us just make this assumption. Okay. So now if you yeah, so the graph is not exactly right in this case. Okay. So okay, so right now what you have, so what do you really want to show here? Okay, so okay, so now, okay, so if we fix this stuff, okay, so if we fix the fix, no, I don't think that's a very good notation, because it seems like I'm just letting n2 go to 0. So yeah, so what I mean is that basically just choose any very small n2, okay, being fixed, okay, and then I'm letting n1 to grow. So in this case what? So in this case, so I'm comparing the hypotenuse, right? So the hypotenuse is, okay, so the hypotenuse is, okay, so the hypotenuse is, okay, so okay, I want a lower bound for the hypotenuse relatively to this n1 and n2, right? Okay, so here, does it has a lower bound here? Does it has a lower bound? Okay, so I know that the hypotenuse is always bigger than this n2, right? So whatever the n2 it is always bigger than this n2. So can I just say that in this scenario that this k just 1, right? Can I just say that? Yeah. Let me think. Yeah, I think so, right? Because yeah, I think so because if you're letting, yeah, because wait, shoot, it has to be n1. Okay, my bad. Okay, it has to contain n1. Okay. Okay, so. Right. Okay. So what happened? So yeah, so that's okay. So it has okay. So okay. Okay. So okay, I think this one, this ideology. Okay, so let's see that whether can I think here, like if we just consider this scenario, right? So I think you can just pick the k to be any like any safe number, right? So any number so that okay, so that's I think wait. Wait, you may have let's see 0.9. Is that okay? Okay, so it's 0.9 works. If I pick k to be 0.9, then what would happen? So if k is 0.9, then you may have the okay. So okay. Okay, I think the key is that how do I really account the part where they are so this n2 is getting added like vertically, Okay, so in this case, okay, it is like what? It is like you have like a long stick, right? And then you are just adding one, and then you adding one up, right? Okay, so I know that here it has exactly the length of like n1, right? Oh, sorry, yeah, n1. Okay, and then you add another. You add another one. Yeah. So you so what happened to the length? So it's just like n1. Okay, so let me just do it algebra. So if you have n1, and then let's say let's just keep it 1, okay, and then which is, and then you are okay. So this one squared, and then plus 1, and then you take the square root, right? So this is the L. Okay, so if I write one more step, it's n1 squared plus 2n1 plus 2. Okay. And so this is the hypotenuse. So does this have something to do with kn1 and kn2? I mean, this n2 we just okay. I mean, this one is definitely bounded below by this guy, right? So yeah, so this one is definitely bounded below by okay, that sounds nice, I think. Oh yeah, because yeah. Okay. Okay, so now what happens if I add the n2 to it? Yeah, what happens if I change it to that? Oh, sorry, n2 squared. Okay. I think it will still work, right? I think this argument will still work. Okay. Okay. Yeah, so this one is still bigger than, yeah. Okay, so I think now maybe you can do it after like a rescale or something, that you can figure out this constant k. Okay. Okay, so let's see. So here our assumption is that we are assuming this w omega 1 to be just 1, right? So let's just make it. Okay, so what happened for the general case? Okay, so okay, so for the general case, what do we do? So okay, so for the general case, what we do is that we just divide it by the, wait, how do we do? We divide by the magnitude. We divide by its magnitude, right? But okay. 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 So here, okay. So let's see. Okay. So general case. Okay. This yeah. So this may not be the general case, but general case. Okay. So I mean the general case for this scenario. Okay. Maybe I would say general. Okay, so general. I think maybe it has something to do with. Okay, never mind. So. Maybe you write half plane. Yeah. Okay. Okay. So now, what we do is that. Okay. So then this guy becomes. Okay. So what I do is that maybe let me just pull out the modulus of omega 1. Shoot. Okay. Yeah. Times the modulus of n1 omega 1 over the modulus of omega 1 plus n2 omega 2 over the modulus of omega 1. Okay. So okay, so then this is equal to modulus of omega 1 times square root of, wait, shoot. Okay. I don't think hold on. Okay, because, yeah. Okay, so because, again, we are assuming this one, okay. So here is just, okay. So, let me think. Okay, so this is just N1, okay, so this is just N1. And then, so this is what? Okay, so this is just the n2 times, okay, so here I have x2, iy2, right? So x2 over modulus of omega 1 plus iy2 over modulus of omega 1, right? Okay, so this is equal to what? Oh, yeah. Okay, so now I can do the argument here. So, wait. Okay, so. Okay, so here I'm having some trouble here. So, I don't think it's the same argument as I made here, right? So, okay, so here I'm making a very nice assumption that this n2 it has length like. Okay, so here I'm making a very nice assumption that this omega 2 it has wait. Okay. I think yeah. So here I'm having a very nice assumption about this omega 2 that it has basically in order to have the n2 appear here, right? Yeah, so I'm having the slope to be, I'm having the x component to be 1. Okay, I'm having the real component to be 1. So, so what? Okay, so yeah, so I'm having the real component to be 1. So that allows me to yeah. So okay, let's see what we can get here. Okay, so here this is the modulus of omega 1, and then here, so okay, so this is the real part, right? N1 plus N2. Okay, so x2 over modulus of W omega 1 plus, so the imaginary part is N2, so I N2 Y2 over modulus of omega 1. Okay. So this whole thing is equal to what? This whole thing is equal to the, okay, so modulus of omega 1 times the square root of, okay, so you have the, okay, so now we have the N1 plus N2 times x2 over modulus of omega 1 squared plus this guy squared, right? N2 times y2 over omega 1 squared. Okay, so this should be our L. Okay, so okay. So these N1, N2, are they real number or they are just they are should be positive number or just any real number? Okay. So I think I made another mistake here. Okay, so this N1, N2, it should be in terms of the absolute value. Okay. Okay. Okay, yeah. Yeah, so I was thinking about all the positive values when I was doing this. So, did I miss something here? Okay, so I know that, so these are all like taking, okay, so these are like doing something inside, right? Okay. I don't think there is anything that I missed here. Okay. Unless I think there might be a case where, yeah, so where these two. Yeah, so I mean like okay, so here in some case. Wait, shoot. So what happens if this N1, N2 is negative? Do I really have this? Oh, okay. So if it is negative, then this is definitely chain, right? Yes. Okay. So so here I'm implicitly assuming that these N1, N2 are all positive. You want to add them together to form the sum like that. Okay. Okay. So these are more complicated. Okay. So maybe let me add like a N1, N2 positive. Maybe let me just add this assumption temporarily. Then this makes sense here. So then there's no trouble here. Okay. So okay. So now so let's focus on this one first. So okay, so since I'm assuming that this N1, N2 are all positive, so I think I can do another trick is that, so this is bigger than or equal to modulus of omega 1 times just the N1 plus N2 x2 over modulus of omega 1. Okay. Yes, okay. So yeah, so here yeah, so here you can take a minimum over this x2 and x2 over omega 1 and this 1, right? And because you are multiplying, so this is positive, so you are multiplying it by a smaller number, so it's still a smaller number, right? Okay. So therefore, what you get is that you get a small number. If you have a number, right? That's the border. So why you slowly boring. Okay.